going to start with this slide, which plots physiological relevance versus biological specificity. On one extreme, you have patients, which is where you want your drugs and therapeutic strategies to work. But the discovery process begins much further upstream here with cell culture models. So targets identified using cell culture models are ultimately validated using higher level models until you get to clinical trials. But this pathway is not very effective. Recent data, particularly from drug discovery studies, suggests that 30% of these drugs fail because they're still toxic. They're toxic in humans despite promising preclinical studies which show they're not toxic. And another 60% of these drugs fail due to efficacy issues. So all major funding agencies, including NIH, Department of Defense, NASA, and the National Science Foundation, have focused their efforts on trying to make better preclinical models, particularly what they've defined as tissue chips, which is what I call our models now, tissue chip models. So these models utilize human cells, organize these cells much in the same way they are in the body, and then try to recreate critical interactions that these tissues and organs see with other tissues and organs, at which point these tissue chips put together become what you call a microphysiological system. And then use these as a platform for initial validation. And if these advance sufficiently, maybe even bypass animal studies before clinical trials. In the context of cardiovascular disease, construction of these tissue chip models is been limited because two issues. One is the lack of relevant human cell types, and the other is systems to recreate the complexity that you see in the beating heart. So just looking at cells, I've just listed sources of cells and the stages of maturation. Typically, we've used neonatal or adult cells from sources like chick, mouse, or rat for our preclinical studies. There's also cell lines available, both contractile and non-contractile cell lines, but these are very different from the adult human cardiomyocyte. There's also a human cardiomyocyte, ventricular cardiomyocyte cell line which is available, which is a non-contractile phenotype, and it does not accurately model what you see with adult cardiomyocyte. It wasn't until discovery of methods to generate induced pluripotent stem cells and then differentiate these stem cells into cardiomyocytes that we have a renewable source of human cardiomyocytes. So these are human iPS cardiomyocytes, but these again, with regards to their maturation status, is still an embryonic or neonatal phenotype. They are very different from an adult cardiomyocyte. Specifically, if you look at their electrophysiological function, they have much higher resting membrane potential. They also have very limited expression of this ion channel KIR 2.1, which is necessary for the inward rectified potassium current, so they beat spontaneously. In terms of calcium handling, the majority of the calcium enters the cells through the sarcolemma, as opposed to calcium released from the sarcoplasmic reticulum. In terms of mitochondrial numbers and organization, they're very different from adult cardiomyocytes. In terms of energy, they rely on glycolysis and oxidative phosphorylation, whereas adult cardiomyocytes rely on fatty acid oxidation. Also, in terms of function, they have a negative force-frequency relationship, whereas adult cardiomyocytes have a positive force-frequency relationship. And treatment with a beta agonist like isoproterenol does not elicit a positive inotropic response. So these cells are very different from adult cardiomyocytes. So I've got a cross-section of the beating heart. First, it's three-dimensional tissue, which is really well organized. These myocytes have preferential orientation. But if you look at current cell culture techniques, we use 2D cell culture, which is not representative of what you see in the adult heart. People try to do 3D cell culture, and the example I have here is a spheroid. The spheroid is 3D, but the organization is lost. But several groups have used hydrogel-based techniques to embed these cardiomyocytes and attain preferential orientation. Another thing I want you to notice for the heart is there's electrical impulses. There's also changes in stretch and pressure with every cardiac cycle. In terms of methods for culture of these cells, I think more than 95% of researchers using cardiomyocytes use culture dishes, which is very different from the dynamic environment you see in the heart. Some groups have tried to incorporate the fluid inflow and outflow from the heart by putting it on a rocker platform. Other groups have used commercially available equipment to stretch these cells or subject them to electrical stimulation. But none of them have truly captured the dynamic environment you see in the heart. So this is the problem we seek to address, is develop relevant models to culture these cells. They behave much like they do in the adult heart. So in order to do this, we develop what we call the Biomimetic cardiac tissue model. And this is just a simplified schematic of what really goes on with this model. This is really to mimic left ventricular function, but in reality, this model can mimic pressure volume loading associated with any chamber of the heart at any stage of development. So the cell culture model itself has a cell culture chamber, which has a thin flexible membrane at the bottom, which can stretch in response to filling. So when fluid fills the chamber, it stretches to mimic filling in the ventricle. Once filling is complete, we induce contractions using an external source of compressed air, which returns the membrane to its original position, causing the fluid in the chamber, the pressure of the fluid in the chamber to increase. And then ejection occurs when the pressure in the chamber can overcome the systemic resistance of the afterload that we set. And this cycles over and over again, reproducing the left ventricular pressure volume loading that you see. This is just more details regarding the cell culture chamber. This is 2 posts which we use to anchor our tissue, 3-dimensional tissue. The posts are anchored on top of a thin flexible membrane. We use a mold, and then we introduce cardiac cells in a hydrogel, fibrin gel, which after compaction looks much like this, with the allografts removed. So this is just to show you what really happens when the stretching happens during the filling. Is the post in the state of rest. When it fills, there is a obstruction at the bottom, so the stretch occurs only at the edges, pulling the posts apart to induce stretch on these 3D engineered tissue. We also have a prototype to subject these constructs to electrical stimulation. And this electrical stimulation can be accomplished in synchrony with mechanical loading. So this is the pressure within the chamber. You can synchronize the electrical pulses to coincide with the onset of systole. So this is something we're in the process of integrating within our system, but this is just a prototype of what we have. So what you see here is this system with a 3D piece of tissue suspended between the posts, subjected to pressure volume loading within this. No electrical stimulation yet, but this is the model that we have currently. So there's 2 issues we really seek to address. First is the source of cells. We have human-induced pluripotent stem cell-derived cardiomyocytes, which is still immature. So can we mature these cells so they represent adult cardiomyocytes? And then the second issue is, if we do have a source of human adult cardiomyocytes, can we then build disease models? So I'll start with the maturation process of these induced pluripotent stem cell-derived cardiomyocytes. I just have a busy slide here, but I'm not going to go through everything here. So from the time the endocardial tubes fuse to form the linear heart tube, looping, and then chamber formation and development of a complex organ, biomechanical signals are very important. So as the embryo grows, it requires blood to sustain itself. So as the embryo size increases, cardiac output needs to increase. Initially with a small organ, this is accomplished by an increase in heart rate. But as the organ grows in size, the stroke volume can increase, and that's how the cardiac output increases to sustain the embryo. There's been several studies, particularly in sick heart development, that show that even small changes in preload or afterload can result in congenital heart defects. So just based on literature, and based on what we know from heart development, it seems like pressure volume loading, conditioning of pressure volume loading is extremely important in terms of heart development. Yet, all differentiation protocols for iPS-derived cardiomyocytes are accomplished in static culture. So maybe the reason why we can't get adult cardiomyocytes is because we don't impose these mechanical loads at the right time to enable them to differentiate efficiently into adult cardiomyocytes. So this is just a differentiation protocol for iPS cells into cardiomyocytes. This is accomplished primarily with modulation of the beta-catenin Wnt signaling pathway. Initially, these iPS cardiomyocytes are induced into mesodermal precursors and then differentiate into cardiomyocytes. What I've done here is tried to overlay the corresponding stages of heart development with this differentiation protocol. So I'm just looking at the different stages of heart development. We arbitrarily classify these into early and late cardiac development, embryonic heart development. And the event that we use to distinguish these two phases is the establishment of the SA and AV nodes. And the reason for this is, prior to this, we don't need electrical stimulation. Past that point, we would need electrical stimulation. So initially, we're focusing on the early development part. At that stage, what these cells really see is initially peristaltic flow, followed by gradually increasing pressure volume loading. And these are still at embryonic levels of pressure and stretch, and for a duration of 7 days, which is to coincide with what happens with the differentiation protocol. What we expect to see is these cells are still spontaneously beating because the nodes are still not formed to drive these. But what we really want to see is if there's hypertrophic and hyperplastic growth of these cells. And then in terms of structure and function, we want to see maturation. And all the data I'm going to show you today is unpublished. It's actually data that was generated recently. So a lot of it's preliminary, but there is evidence to suggest that what we're doing might work. So this is the pressure volume loading that we subject these cells to. We start off with extremely low levels of pressure and stretch, and over a period of 3 days increase it. And then at day 3, we get to the final pressure volume loading levels, and we maintain it in that state for an additional 4 days. And these constructs are made out of fibroblasts and iPS-derived cardiomyocytes, very early stage of differentiation. As soon as the cardiac differentiation of iPS cells begins, we put them within these constructs and then subject them to pressure volume loading. So the first image I'm going to show you is just immunofluorescence microscopy. On the left, on your left, you will see the static controls, and on your right, you see the stimulated samples. And this thing right off the bat, the stimulated sample appear to be a lot bigger than the static controls. And then we stay in here for human cardiac troponin and alpha-sarcomeric actin. You see just the total amounts and the alignment is significantly better with the stimulated samples as opposed to the static controls. These are some preliminary TEM images. On the top, what you see is the extracellular matrix. It appears that mechanical stimulation aligns the extracellular matrix. There is good sarcomeric organization both with the static controls and with the stimulated samples. We see accumulation of lipids in the static controls, but not with the stimulated samples. And then with a higher magnification image of the sarcomeres, we see probably the beginnings of an end band. We also did some preliminary gene expression profiling, particularly looking at genes responsible for hypertrophy and structural maturation. GATA4, myosin light chain, myosin heavy chain, and CAM kinase 2B are all statistically significantly upregulated in the stimulated samples as opposed to the static controls. We also looked at this potassium channel for the inward rectified potassium current. These cells are still spontaneously beating. We didn't expect to see a significant change, but if we do go further along this pathway, late stage maturation, we should see a statistically significant difference there. Finally, we also looked at force frequency response. So this is increasing the pacing frequency and then looking at fractional shortening. What you'd expect to see with adult cardiomyocytes is an increase in the fractional shortening as you increase the pacing frequency up to 1.5 hertz. After that, it drops off. With these iPS-derived cardiomyocytes, we see an increase in the fractional shortening up to 1.3 hertz, and then it drops off. I've got 4 videos here. I hope these play. So these are the static controls. And the first one's in 1 hertz and the other one's in 1.3 hertz. You should really not see any difference between those. If anything, the 1.3 hertz has got much lower fractional shortening compared to the other. But with the stimulated samples, you clearly see that the fractional shortening, which is obtained using video analysis of these videos, I've actually changed the contrast here so you can actually see the fiber move a little more. But you can clearly see that the fractional shortening is increased at higher frequencies. So with this, I'm going to switch gears a little bit and talk about disease modeling using these, the biomimetic cardiac tissue model. And we didn't want to wait until we had a mature phenotype. We wanted to get these models up and running, so if we do get a mature phenotype, we could just put them in our system and we'd have relevant models. So prior to getting into pathological hypertrophy, I just want to explain physiological hypertrophy first. This happens postnatal heart development after exercise. Normally you'd see enhanced cardiac function, little to no fibrosis, a normal gene expression, proportional increase in a proportional chamber enlargement. By this, what I mean is the wall thickens, so does the volume of the chamber. In terms of the cardiomyocytes itself, you should see a proportional increase in length to width. There's increased fatty acid utilization, no oxidative stress or electrophysiological dysfunction. Contrast this to pathological hypertrophy, and this can occur in two ways. The first one is pressure overload due to conditions like hypertension or aortic stenosis, which would result in concentric hypertrophy. This is associated with diminished cardiac function, an increase in fibrosis, activation of fetal gene programs, an increase in the chamber wall thickness. The volume is preserved. And in terms of cardiomyocytes, sarcomeres are added in parallel, so the myocyte itself becomes thicker, not longer. There's a switch to glucose, there's oxidative stress and electrophysiological dysfunction. Pathological hypertrophy can also occur as a consequence of volume overload due to valve dysfunction primarily, congenital heart defects, arteriovenous malformations, all contribute to volume overload or eccentric hypertrophy. Again, you see diminished cardiac function, but instead of fibrosis, what you see here is ECM degradation. This, again, once again, activation of fetal gene programs. There's an increase in the chamber volume, not necessarily a change in the wall thickness. So these myocytes become longer as a consequence of adding sarcomeres in series. There's a switch to glucose once again, oxidative stress, and electrophysiological dysfunction. So what we want to do is try to see within our models if we reproduce the hemodynamics associated with normal function, pressure overload, volume overload, if you could recreate structural remodeling particularly that you'd see with each of these conditions. So to do this, we use H9C2 cardiomyoblasts in conjunction with cardiac fibroblasts, mix them together and seed them in a hydrogel within our systems, and then subject them to each of these conditions. Once again, these are just preliminary data, but I think they make a case for what we're saying. Histology after 2 days did not really show us any difference in each of these conditions, so we took them out to 7 days. And this is the constructs in our system after 7 days of stimulation under each of these conditions. I don't know if it's absolutely clear or not, but the static control and the normal look very similar. With the pressure overload sample, you should be able to see that it's a little thicker than the other samples. With the volume overload sample is where we saw the most exaggerated changes. This fiber became so long in length that when we brought it back to normal position, the fiber kinked because it just extended during that course. So quantifying this in terms of fiber aspect ratio, by fiber what I mean is the construct itself. Static and normal, there's really no changes there. So normal is something which you'd consider physiological hypertrophy, whereas pressure overload and volume overload, pathological hypertrophy. Pressure overload was significantly thicker, volume overload was significantly longer. Preliminary gene expression profiling, and then once again, we probably need more sample size for this. Looking at genes responsible for fibrosis, cytoskeleton, ECM remodeling, and oxidative stress. With pressure overload, we see a statistically significant increase in collagen 1 and TGF-beta, along with SOD1 and SOD2, and TIMP1 and TIMP2. With volume overload, we saw a statistically significant difference in desmin, along with SOD1 and SOD2. And finally, this is probably the last set of data I'm going to show, is we just looked at Mason trichrome staining to just see what these fibers look like. So this is static and normal. There appears to be little to no difference between these two conditions. Whereas the pressure and volume overload, we really didn't see significant changes. Particularly the pressure overload, the fibroblasts are all localized to the center. You see the increased proliferation of these cells, and there is significant fibrosis. And this is just with pure pressure overload. We did not do anything else except change the loading conditions. With the volume overload, it may be difficult to see, but these cells are much longer than they are with the pressure overload. We also did one additional condition where we did pressure overload in conjunction with TGF-beta. So this is normal pressure volume loading. This is static controls of TGF-beta. This is pressure overload TGF-beta. And we're staining here for collagen 1. It looks like there's significant upregulation of collagen 1 when you combine pressure overload with TGF-beta signaling. So this is my last data slide. I'm going to summarize. So I hope I've convinced you that the BCTM represents the state of the art with cardiac tissue chips. You can recreate hemodynamic loading and unloading seen with embryonic heart development. iPS cardiomyocytes subject to hemodynamic loading as seen during early heart development. associated tissue growth and structural and functional maturation. The BCTM, or the Biomimetic cardiac tissue model, can also be used to model disease conditions as with pressure and volume overload. And the structural and to a certain extent the molecular remodeling that you see with pressure and volume overload, we could reproduce with our system. So with that, I'd like to acknowledge Aaron Rogers in particular, who's the PhD student, who was a PhD student in my lab. And this is all part of his thesis. All the data shown here today is part of his thesis. He's now a postdoc in my lab. And various collaborators, Dr. Ram Kanavan was involved in both these studies. Dr. Fast has been helping us with the integration of electrical stimulation with these systems. And then we tried to use these models in conjunction with various other groups.